pencil rental.
It's a red pen. I like a pen.
All right, so today we're going to talk about velocity and other rates of change. So the instantaneous rate of change of a function, f, with respect to x, at a, is the derivative f prime of a if it exists. Right? Remember, we know all kinds of places where a derivative doesn't exist. That's a good thing to review while we're talking about that. Where are the places where a derivative is not going to exist? Give me just one. Yes? Right. If a function is not continuous at x equals a, then it's not differentiable at x equals a. Very good. Someone else, give me another one. There are three of them. There's three of you. Ha ha.
If the function makes a cusp.
Okay. If a function has a cusp.
Yeah.
What would be another one?
I have no idea.
Vertical tangent or corner. A cusp is a type of vertical tangent, but a corner, right, where the left-hand derivative and the right-hand derivative at that point do not agree with one another. Okay? So, let's take a look at this example. If A is the area of a circle, find the rate of change of A with respect to the radius r when r equals 5 centimeters. Use correct units.
It's physics.
Yeah, most of calculus, or at least a fair bit of it, I shouldn't say most, was designed to answer questions that physicists couldn't figure out on their own. No. At the time, most physicists were mathematicians also. There wasn't quite the division that there is now.
They weren't just like bored with math, so needed something more exciting, so they went to physics.
Well, it used to be that most of the philosophers were mathematicians also, like René Descartes. You don't know who René Descartes is? Yes, quite French. And I probably say his name badly, but he was a philosopher, a mathematician. Have you ever heard of the Cartesian plane? So anytime you graph, you're graphing on a Cartesian plane.
Named for to name it after him.
Because he was one of the first ones to come up with a system of graphing where you have two perpendicular number lines intersecting, making a grid. He was one of the first ones to do that.
Interesting.
All right, so the area, he also was a philosopher who said, I think, therefore I am. Well, so at the time, people were like, do I really exist, or am I just, imagining this? And he's like, well, I know that I think, and since I think, I must exist. And then he built everything up from that.
I know Pythagoras. He taught us about that.
About Pythagoras, yeah. So area is pi r squared. So the derivative of the area with respect to the radius, dA dr, pi is a constant, so I'm going to keep it, times the derivative of r squared with respect to r is 2r. So that's 2 pi r.
That's pretty nifty.
Which is what? Circumference. And when you think about it, if the radius of a circle expanded just a very little bit, can't you sort of think of that as like adding on another circumference further out? Yeah. And the units for this, since it's the change in the area, that would be square centimeters per centimeter. Nope. Square centimeters per centimeter. Which is also why, and it's not really a big deal, but when you say in physics, feet per second squared, what the heck is a squared second? You really mean feet per second. because acceleration is the change in velocity with respect to time.
Square second, you're going up and down at the same time.
Yeah, I'm like, wait a minute, I'm squaring time? How does that work exactly?
That's a t-shirt right there.
Yeah. What exactly is a square second? All right, moving on. Motion along the line. So in BC, we'll eventually get to two-dimensional motion. For this class, we only do one-dimensional motion, where it's only moving along a line. So suppose an object is moving along a coordinate line so that we know its position S, and I'm not sure why they use S for position, but every book I've ever read does. So S on that line as a function of t, S is equal to f of t. The displacement of the object over the time interval from t to t plus delta t is delta S, which is f of t plus delta t minus f of t. And the average velocity of the object over that time interval is given by this equation, v sub av is equal to delta t over delta s. So that's f of t plus delta t minus f of t over delta t. That should remind you of something.
Derivative.
It is the derivative. Not quite.
Nice, pretty close.
What will we need to have here to make the derivative? The limit as delta t goes to 0 to get the instantaneous. So since this isn't the instantaneous rate of change, what is it that this is finding? This is the average rate of change.
That's why it's v and f.
This is the average rate of change of the position function. Because the rate of change in position is velocity. So the average rate of change in position is the average velocity. Well, if that's true, then the instantaneous rate of change in position is the instantaneous velocity, which will just be our derivative. V of t is equal to ds dt, which is the limit as delta t goes to 0 of f of t plus delta t minus f of t over delta t. Could we have done this with h? Yes, we could have. Right? It's just another application. All right.
Math is so smart.
Yeah, I like to say a lot of times in math we're explaining why things in physics work.
Yeah.
So when an object is moving forward, that is when s is increasing, so anytime s is increasing, the object is moving, we say it's moving forward. The velocity is positive. So if s is increasing, velocity is positive. When the object is moving backwards, that is when s is decreasing, the velocity is negative. That makes sense, right? So, if we're interested in how fast an object is moving, without regard to direction, we want to know about speed. Remember, speed is the absolute value of velocity. Velocity has a direction. Now, for things that are moving along a line, the direction is either just positive or negative. So, in addition, the rate at which a body's velocity changes is its acceleration. Acceleration is the derivative of velocity with respect to time. So a of t is dv dt, or d squared s dt squared. It's the second derivative of position. So that's the instantaneous rate of change of velocity. with respect to time. It's so much quieter when all of the ACs outside shut off. I kind of like it. I don't know.
Do you like teaching in this room? Because of all your.
I'm not as distracted as my students are sometimes. All right. So I think this is actually a thing that's helpful even in physics. If you'll think about acceleration as being the instantaneous rate of change of velocity, and velocity as being the instantaneous rate of change in position, I think it makes some things make more sense. Okay? So we're going to look at an extended problem here. A particle moves along a line so that its position at any time t greater than 0, greater than or equal to 0, is given by s of t is equal to t squared minus 4t plus 3. I know I'm going to need that again in a minute. We're on another page, so might as well write it down. Where s is in meters and t is in seconds. So find the displacement of the particle during the first 2 seconds. Well, the displacement, and by the way, displacement used to be on the AP exam for calculus, they didn't ever use it. Now they're like, why didn't we ever use that? And so they started using the term. So the displacement, it'd be nice if I spelled it correctly. Is the change in position. So that's going to be 2 squared minus 4 times 2 plus 3 minus 0 squared minus 4 times 0 plus 3.
What does that say? Delta
S.
Why is it an S? Oh, because it's high.
Because the position is given as S.
Why?
I don't know.
I guess F doesn't really make that much more sense, but
What about P for position?
that would make sense.
That would make sense to me too. All right, so that's going to be 4 minus 8 is negative 4, and everything else is going to cancel out. So this is moved 4 meters to the left. All right, find the average velocity during the first 4 seconds. Well, that's the average rate of change in position. So the average velocity is going to be the position at time 4. So that'll be 4 squared minus 4 times 4 plus 3 minus 0 squared minus 4 times 0 plus 3 over the change in time, which is 4. Turns out the average velocity during that time was 0. You're like, wait a minute, how did that happen? Well, what was the displacement? Notice the numerator of this is the displacement. What was the displacement? 0. So basically, it went somewhere and then came back. It's like if you swim a lap in a pool, your average velocity is 0. Because you have no displacement. Now, your average speed is something else. But your average velocity is different. Okay, moving along. Find the velocity of the particle when t is equal to 4. Well, I know that s of t is t squared minus 4t plus 3. So v of t is s prime of t. And whenever possible, I write things this way to announce, hey, I'm taking the derivative. Make it clear to everyone exactly what it is that you're doing. So that'll be 2t minus 4. So the velocity at time 4 is 2 times 4 minus 4 is 4 meters per second. Find the acceleration of the particle when t is equal to 4. Well, a of t is v prime of t. And I wouldn't probably write this, but just because we're talking about it, it's the second derivative of the position function. So that's going to be 2 all the time. So then a of 4 is 2. All right. So at what value or values of t does the particle change direction? Okay. This is one where students frequently learn half of the right idea, and it gets them in trouble later on. Okay? When does a particle change direction? That's the wrong answer. That is half of what happens. I'll demonstrate to you. Okay? I'm walking along a line. Okay? What is my velocity now? Did I change direction?
When you're left-handed, no?
No. So, right now, I'm walking forwards, right? What kind of velocity do I have? Positive. Change directions, I need to have a negative. So, in order for the particle to change directions, the velocity has to change sign. Now, in order for the velocity to change sign, the velocity has to be 0 at that point. But just because the velocity is 0 at a point doesn't mean that we're going to change direction. Okay? It's subtle, but what people will say is exactly what you said. The velocity is 0, it changes direction. So that means every time you pull up to a stop sign, you change direction.
Yeah, I always do right turns.
You always start backing up.
Maybe if you're in the manual,
So let's write that down.
If I'm going uphill in the manual car, sure.
I guarantee you, buddy, you're
The particle changes direction when the velocity changes sign. The particle will change direction when the velocity changes sign. Well, we already know the velocity function is 2t minus 4. And yes, we will set that equal to 0. So that would imply that t is equal to 2. So we know the velocity is 0 at that point. And since this is a linear function, where the graph of a linear function touches the x-axis, does it ever go back the same direction? No. So we know that the answer will just be at t is equal to 2. But if you have any higher power, you should really look. Because you did some of these, I know, in Algebra 2 or Pre-Cal, where you had some cubic function that did this. If this was a velocity function, and this was -2 and this was +3, where would the particle change directions? This is the velocity. The velocity is positive, the velocity is 0, the velocity is positive again. At 3, the velocity changes direction. So I'm not asking when does the velocity change direction, I'm asking when does the particle change direction. You have to really be thinking. Okay?
I always miss those graphics.
So this is not the graph of the position. This is the graph of the velocity. So if the velocity is 0, so if the velocity is positive, then 0, then positive again, no change in direction. Here the velocity is positive and now it's negative, change in direction. So the velocity graph must pass through the t-axis at that point. But it's better to say the velocity has to change sign.
Well, how will we calculate that?
How will we know that? So one way you could do it is you could graph the velocity function.
So we just
To graph y equals 2t
calculate.
minus 4. If it's more complex than that, if it's a quadratic, and you should be able to graph most polynomials fairly quickly without a calculator. So what you can do, if it's a continuous function, is you can look at a value just before the 0 and just after the 0 to see if there's a sign change. Does that make sense? So like here, if I look at t is equal to 1, the velocity is negative. At t is equal to 3, the velocity is positive. There has been a sign change, and the only place where the velocity was 0 was at 2 in between those, so that must be the place where the particle changed directions. Okay? All right. Use parametric graphing to view the motion of the particle on the horizontal line y equals 2. All right. So grab your calculators. So I'm going to change the mode to parametric.
What's parametric?
Where the x, the equation for the motion in terms of x and the equation for the motion in terms of y are given separately. You did it last year in pre-cal.
Oh yeah,
We used to physics.
last year. Not physics this year.
So the position function was, so I'm going to be moving along the line y equals 2. So my y equation is just going to be 2 all the time. And then here I'm going to have t squared minus 4t plus 3. The nice thing is when you change, it automatically changes your x to t. And so that I can watch the motion, I'm going to move over here and change this to, oh, I missed it. Go back. The ball. Right? And I'll do a zoom standard just so I can see it.
Can you slow down the ball?
Yes, you can. by going into your window and making your t-step smaller. So right now it's a little over 0.1, and notice the default here is that the t minimum is 0 and the t maximum is, do you recognize that? 2 pi? Because when you guys did like ellipses and circles and all that stuff in parametric mode last year, most of the time you needed to go from 0 to 2 pi to complete the ellipse. So yeah, we can slow it down. We can make it glacially slow if we want to.
What's the t-step do? Like,
So what it's doing is, it's how often is it calculating?
Because can't that on some graphs it affects like the accuracy of it or something?
Yes, if you have too large a t-step, what's happening is your calculator doesn't actually graph curves at all. It plots a whole bunch of points and it connects them.
Oh, so the fewer points you have,
The more jagged it might be. So it's like when you have a pixelated picture. So now I have made this go a lot slower. Oh gosh, that's hard to watch. And the thing is, it's going to slow down even more as it continues to move left. Still going.
my t-step of 0.02 was quite nice.
Yeah, I did 0.01. It's a little slow. But that's an excellent question.
Probably find the pencil faster than the airplane.
All right. Any questions about that?
Guess not.
Guess not. We didn't quite get to that last question. Oh well.
It's a Tuesday problem.
Y'all have a great weekend.